In this video, we're going to look at projectile motion, and that could be anything such as, somebody throwing a ball. Maybe it's a ball going in the air, and the ball could be hitting the ground, or it could maybe hit a mountain or a hillside. Projectile motion could also include perhaps a skier jumping and hitting, the slope at some point. That would come under projectile motion. So there's several things. And real quickly, we'll give a little bit of background. So what we're going to do when we handle these problems is we're going to assume that there's no air resistance. And so that means the acceleration, the x direction, is going to be 0. So we're assuming no air resistance, so the ball is going to be able to just keep moving at the same speed in the x direction. Again, so what that implies is the velocity in the x direction is going to be constant. It'll be whatever it was when the ball was originally thrown or the object was originally thrown. In the y direction, there's acceleration due to gravity, which is going to be, if it's in English units, negative 32.17, or you can round this to 32.2, or in SI units, it would be negative 9.81 meters per second squared. And of course, the projectile will reach its maximum height when the velocity in the y direction is 0. Of course, as the ball is going up, the velocity in the y direction will keep getting lower and lower and lower. Then it'll get to 0. Then it'll go negative. So the max height, will of course occur when the velocity in y direction is 0. And the method that we're going to use, and this is the most versatile method, is to find an equation for the path of the ball. Ultimately, we want to find an equation for the path of the ball in terms of y as a function of x. Now, again, if the problem is very simple, you don't need to do this, but I think it's good to get used to doing this because this will work in all cases. We're eventually going to get to y is a function of x, and that will determine the path of the ball. And then also, if the landing surface is not flat, we're also going to find an equation for that surface. Y is a function of x. Then we'll set those two equations equal. But near the beginning, we're going to work with the basic equations for motion. We're going to use the basic x equation, which is going to be x equals the initial position of x times the initial velocity of x times time, plus 1/2 the acceleration in the x direction times time squared. Same as for y, we'll have y equal y naught plus, again, that's going to be the initial position y, plus the initial velocity in the y direction, plus 1/2 at squared, again, where a is the acceleration in the y direction. Of course, as I mentioned, this is almost always going to be gravity. So again, we'll look at a couple of cases. We'll look at the case in which the ball is going to land on a flat surface. And also, we're going to look at the case where the surface is going to be sloped. And that pretty much will cover all the possibilities, because if we know how to handle even just a straight slope, same method will work for pretty much whatever hillside or terrain you have here. So let's start with this problem. Suppose a boy releases the ball from a height of 5 feet at a velocity of 22 feet per second at an angle of 28 degrees with the ground. Find the maximum height of the ball and find the distance at which the ball lands and the velocity at which it lands. So again, the distance at which it lands is going to be, let's say it's going to go up here. It'll be like this distance from here to here is what we're looking for. And so there's several things we want to do. Number one, first determine the coordinates and determine 0, 0. So determine the 0, 0 point. So again, we're assuming we're going to have X and Y components. And so we'll have, our coordinates are going to be X and Y. But what is the point 0, 0? And again, you could make the point 0, 0 here where the ball left the boy's hand, or you could make it right below where it left his hand on the ground. Now, depending upon the problem, one may or may not be a little bit easier than the other, but usually I would pick right below here on the ground where the ball is being released. In other words, I'll make this 0, 0 down here, make this point right below where the ball is released, 0, 0. Then that means where he's actually releasing the ball is going to be 0 on the X and 5 on the Y. So first thing we have to do is determine where 0, 0 was. I picked this here. You could as well have picked this up here. Now, the only thing is, if you would have picked 0, 0 here, you just have to remember that the ball is going to hit the ground when Y is -5. The advantage of picking 0, 0 here is when the ball hits the ground, the Y component is going to be 0. So the next thing we have to do, we have to find the X and Y components of the velocity. So now the easiest thing to do is, so if you want to find the components, see what angle you have and where it's measured from. So here we have that 28 degrees measured from the horizontal. So in other words, the 28 is adjacent to the horizontal. In other words, it's adjacent to the X coordinate. So we could say the initial velocity, and I don't know, we want to call this, before we called that Vx naught. That will be whatever velocity we have here, 22 times the cosine. Of 28 degrees. Again, because it was measured from, this was the adjacent side was the X. Remember, the adjacent is always cosine, so it's 22x, 22 cos 28. Now the Y component will have to be the sine. If that was the cosine, the y component's got to be the sign like this. And when you put that into your calculator, we get VXO is 19.42 feet per second. VYO is 10.32 feet per second. So what that means is if we were to look at this, the 10 1032 here. $19.42 here. Back. And then, so now we can find the equations. So let's take a look at the equations. We talked a minute ago about using our equations. Let me put those over here. And remember we said, so we went for the x direction. We have x equals x naught plus v x naught. Or you could just put v naught because you'll know that it's for the x component. 1/2 axt squared. Now, again, we know that there's no air resistance, so there's going to be no acceleration in the x direction, so that's going to be 0. And notice also our initial position, the initial position of the ball is going to be 0 on the x and 5 on the y. So we know that that's x naught's going to be 0. So it's going to be 0 as well. And then we also know that the x component of the initial velocity is 19.42. So our equation for motion in the x direction is going to be 0 plus 19.42 t, like that. And we can call this equation 1. And then for the y direction, y equal y naught plus vy naught t plus 1/2 ay t squared. Again, use the same equation. Now, again, notice the ball is leaving 5 feet above the 0, 0 position, so the y component is going to be 5 here. And then the velocity in the y direction is 10.32. And now over here, remember, this is going to be acceleration y direction, so that's going to be gravity, so it's negative 32.17. Let me put the negative out front. T squared, like that. So that's going to be the equation for motion in the y direction as a function of time. Let's call that equation 2. Now we're also going to need the velocity eventually in the y direction, because we're going to need to find a place where the velocity is 0. So let's do that. So the velocity in the y direction will be the derivative of this, say call it y prime, of this equation. Remember, velocity is always going to be equal to the derivative of the function. Let me actually write it. Velocity y, the general velocity for y. Remember over here, we just had y naught, velocity of y naught. That was the initial velocity, but now we have to find the general equation, and that's going to be the derivative of this with respect to y, excuse me, with respect to t, and that will be 10.32. We take the derivative of this will be negative 32.17 t. And so that's the equation for velocity in the y direction. Yeah, we don't need an equation for velocity in the x direction because remember, it's constant. Whatever it started with, it's going to continue that way. And let's call this equation 3. So now, as I said at the beginning, we want to find y as a function of x. So to do that, solve for t in equation 1. So we'd go back here and solve for t. And that's going to give us t is equal to x divided by 19.42, or t, if we divide that out, it's going to be 0.05149x. So we solve for t up here. You got it in terms direct. Now substitute that into equation 2. And when we do that, we're going to have y equal 5 plus 10.32, 0.05149x minus 1/2, 32.17, 0.05149x squared. So again, all I did was solve this for t in terms of x, substitute that into this equation. So now we have y as a function of x. And let me just clean that up a little bit. Let me multiply some of these things out. And when we multiply all these out, we're going to get y equal 5 plus 0.53141x minus 0.04265x squared. And we can call this equation 4. So it gives us y as a function of x. Next, we want to find the place where the ball hit the ground. And so we're going to find that x value because it was asking what that position is. Now we have to say to ourselves again, where is the ball going to hit the ground? It's going to hit over here somewhere. And of course, we don't know the x coordinate. We do know the y coordinate since this is level with our starting point, and this starting point here was 0, 0, then y has to be 0 here, because the y component is going to be 0 here because it was 0 here. Now, if you happen to pick your 0, 0 point up here where the ball left the boy's hand, then when you do this step, you're going to have to use -5 here, because if this was if you set this as 0, 0, then this is going to be -5. But then I set this 0, 0, so the y component here is going to be 0. And so to find where that happens, set y equal to 0. And again, we're going to use the quadratic formula. So let me rearrange this equation a little bit. Again, I'm going to set y equal to 0. Let me put the x squares first. So it's going to be negative 0.04265 x squared plus 0.53141 x plus 5 is 0. So I set y equal to 0 in this equation here, and that'll give us the x coordinate when the ball hits the ground. So again, we're just going to use a quadratic formula. And remember, quadratic formula says it's going to be negative b plus or minus the square root of b squared minus 4 times a times c divided by 2a. Negative b plus or minus b squared minus 4 times a times c divided by 2a. And when you do this, you end up getting negative 0.53141 plus or minus 1.06554. And this down here is 0.853. And when you put these in your calculator, this is going to give 18.7215 is going to be one answer because it's plus or minus, and the other one is going to be negative 6.2617. So now the negative would be, if this is 0 and the x negative would be back here. So it's kind of looking back in time. If you were to plot this backward, it's kind of showing where the ball would have come from, if it had followed this path in the opposite direction. So the negative is not relevant in our case here. So therefore, what we're interested in is this one here, the 18.72 feet, 7215 feet. And now we want to find, so that's going to give us the position where it hits the ground. We're going to need also the velocity where it hits the ground. So we're going to need to find the time. So when does it hit the ground? And so we can, probably the easiest thing to do, we could actually go back and use equation 1. Because there we had x was equal to 19.42 t. But now we know what x is when it hits the ground. It's going to be 18.7215, 19.42. So then solve for t. T is equal to 0.96403 seconds. Now to find the y component of the velocity where it hit the ground, we can go back and use that velocity equation that we found a little while ago, equation 3. And plug in that time. So again, remember equation 3 is this one, so we'll plug in for t. And when you calculate that, your y component of your velocity is negative 20.69 feet per second. So now the magnitude of the velocity is going to be the x component squared, y component squared. Now remember there was no acceleration or deceleration in the x direction, so it was that velocity was a constant 19.42. And so if you put that in your calculator, you get about 28.38 feet per second is going to be the velocity. Where this was the x component, that was the y component. Now, next thing we want to do is find the maximum height. And remember, we said the maximum height occurs when the velocity in the y direction is 0. So find max height. And so, and again, let me just write down occurs when velocity in y direction is 0. Again, so we have Vy equals 10.32 minus 32.17 t. And so we'll set that equal to 0, 10.32, 32.17 t. And if we solve for t, we get 32.079 seconds. That's when we reach the maximum height at that point. Now to find the y component, we have to go back to an equation that has y as a function of t. And we can go back, now we're back at equation 2, and we can plug our t in equation 2. And so we're going to have y equal 5 plus 10.32 times t minus 1/2 32.17 t squared, like that. And when we put all that in our calculator, we get y is 6.65382 feet. That's going to be the max height. So again, we found the key in this, we found y is a function of x. We found an equation like that. And then we're going to look at the next problem and see how that's particularly helpful for the next problem. Oh, by the way, I just want to mention one thing back where, yes, we had found this, again, this 18, I sort of moved past it kind of quickly. When we found this 18.72, that gave us that distance. That was actually this distance here, 18.72 was the distance from where the ball was thrown to where it hit the ground. So it'd be that distance like right there. So let's take a look at this problem, which is the first part is very similar, or the first part is exactly the same as the last part. And so we're not going to recalculate a lot of this. The only difference is instead of the ball landing on a level ground, it's going to land on this sloped area here. And so let's take a look at that. Once again, everything else is the same about how he throws the ball. So we've already calculated that equation. So now we have to figure out where the ball is going to hit this slope. And the easiest way to do that is to find an equation for this slope or this hillside here. And to remember, we've determined, or we picked this point right here to be 0, 0. So now we would like to find an equation for this slope region here. So you remember, so if this is 0, 0, then of course this point right here is going to be 7 on the x and 0 on the y. And so we're trying to find an equation for this. Now, we can use the equation of a line. So equation, I don't know what we're going to call this, maybe the hillside. And we can use our equation from algebra y naught is equal to mx minus x naught. Again, remember this is the slope. And this x naught, y naught could be any point along this slope. And so we have a point we know along this slope, this point right here, 7, 0. So we can plug this into our equation. 7 in the x, 0 in the y. This. Then we can just solve this. We can multiply this through, maybe make it look a little bit better. So we have this. So that's going to be the equation of this hillside here. So now if we want to find out where the ball hits the hillside, we can use the equation for the path of the ball and set it equal to the equation for the hillside. And so let's do that. So let me write that down. Again, the reason we can do it because we have the equation in terms of x, where y is a function of x. So find the place where the ball hits the hillside. Set equation for ball equal to equation for the hillside. And so again, we have to go back to that equation where we had y as a function of x. And so let me go back and get that equation. That was this one here. I called equation 4. So we'll do that. And once again, I'm going to rearrange and go put the x's first, x squared first. So I'm going to set this equal to our equation for the hillside. So let me start with this, because see, they're both equal to y. And so what we're really doing, we're finding where the intersection of this curve is with this curve. So we're intersecting this curve for the ball with the equation for the hill. So we'll do this. This is going to be negative 0.04265 x squared plus 0.53141 x plus 5. That's the equation for the ball. Then the equation for the hillside is up here. That was negative 7/2 x plus 49/2. Like that. And then, so now we want to take this equation and just set it equal to 0. So in other words, we want to move everything to the left-hand side, for example, is one way to do that. So let's do that. So let's go 4265 x squared. So here we have an x and here we have an x. So we're going to have to move this over here. Then when we move it over, we're going to end up adding these together. So this is about 3.5 plus 0.3. So let's add, I'm adding this and this. and that comes out to 403,141x. Then also the constants, we have 5, and it's going to be 5 minus 49 halves. And so what's that? That's like 24 and a half. So 5 minus 24 and a half is going to give us negative 19 and a half equal to 0. So once again, use the quadratic formula. And that's going to be negative b. Negative b plus or minus square root of b squared minus 4 times a times c divided by 2a, like this. Now, when you put that into your calculator, this time we get, again, we'll have a plus and minus here, and we end up getting 89.409 or 5.11. Again, those are both in feet. Now, this time it's not as clear because they're both positive, but we can kind of look at this and say that, the ball is kind of rising here. It's probably not going to be dropping down. In fact, when we found before is it's going to go up pretty high. So it's not going to be land over here at this 5.11 feet. So it's going to land way down here where X is 89.409. So, and the question is then, what's going to be the y component when that hits? So remember what this is here. This 89 is going to be the distance from here over to here, wherever it lands. This is going to be 89 feet. Let me put that maybe down here. So this is going to be like 89.409 feet. Like that. And then what's the y component down? Of course, to find that, we can just go back to our equation. We can just use y equals, remember, our 7 halves x plus 49 halves, and just substitute this into here. This, and then y is equal to 288.4 feet. So this is, so the ball hits the hillside at 89, let me round this off, 0.4 feet and negative 288.4 feet. That's going to be this point right over here. That's where the ball is going to hit the hillside.